Welcome to episode 11 of our lesson on an introduction to geospatial raster and vector data with R. In this episode, we will do some manipulation of raster data in R. This is our last episode of working with the Harvard raster and vector data, and it will get into some more complex tasks where we need to work with both the raster and the vector data together. So this is getting into more geospatial analyses where you might need to extract some data from a raster object based on a vector extent. So you might use some of the things we learned in this episode when you need to crop a raster based on a vector, and when you then need to extract some summary statistics or some summary pixel values from that raster. So in this episode, we're going to crop a raster to the extent of a vector layer, and we're going to extract the values from a raster that correspond to the vector file overlay, or that correspond to the space within the vector. We'll also cover how to extract values from a raster that occur within like a set of polygons or that vector data, or that occur within a buffer region around a set of points. So let's get started by opening our RStudio project. So I've opened the RStudio project file. So we have our RStudio environment where we have the console on the left, our empty environment on the upper right, and our list of files associated with this directory on the lower right. I'm going to zoom in so you can see. And as we have before for all of our other lessons, I'm going to start a new file and create a new R script so that we have these files when we want to go back and reference them later. So with each R script, we want to give a few helpful comments in the beginning to remind us what this script is all about. So I'm going to start off with the title of this script, which is that it is for the episode to manipulate raster data in R. This is episode 11. Give it my name, the date, and a brief description about what this script will do. So this script will crop a raster to the extent of a vector layer, and it will extract values from a raster based on overlay. All right, I'm going to save my file into my folder. I will call it episode 11. Manipulate raster. Okay, so now I have the file saved. I'm ready for the other two parts of my setup, which is to load the libraries and to load the data. And again, if you have these packages and data loaded from previous episodes, no need to go through this process again. But if you're starting with a clean environment and a fresh RStudio session like I am, we'll have to take a few minutes to load and get set up. So I'm going to load packages. I'll continue to use the library function for all of the packages. So I'll do library, and within that function, I'm going to do the package name. So I will run through all of those libraries that we've used. And because we're going to work with both raster and vector data, I want to make sure to include all of the libraries that we've seen thus far. So there'll be 5 libraries in total. Library SF, library raster, library RGDAL, DAL, library ggplot2, library dplyr, dplyr. Okay, so there are the 5 libraries. And now we'll load some of the data that we'll be using. Now, there's lots of data that we have loaded and accumulated throughout these episodes. I'm going to load a lot of the vector data from Harvard. I'm going to load one canopy height model, and then I'm going to load the plot locations that we generated from the earlier lesson. So let's start with the vector data as shape files. For loading vector data as shapefiles, I'm going to use the stread function. And the stread function requires us to put a directory or a path name and the name of the file in that function in quotes. So for these 3 files that I'm going to load, I'll use the function stread, open parentheses, and then open the quotes, and within the quotes, do the path name. I'm going to use tab complete for navigating through all of my folders and for selecting the file names. So I'll do this all pretty quickly, but this is the same things that we've seen throughout all of these episodes. So let's start with my AOI boundary harv. At the end here, I'm going to navigate using my mouse and click on that file name. Let's load the lines harv, stread quotes, data folder, vector folder, harv underscore roads. I'm using my mouse to click the shapefile, and then point underscore harv, stread, parentheses, quotes, data folder, vector folder, harv, tower, clicking the shapefile there. So those are the 3 shapefiles we're going to load. We will also load the raster CHM, or the raster canopy height model. For this function, for this data, because it's a raster file, we're going to use the raster function of the raster package. So just like we did with the st function, we're going to use raster, and then within that raster function, give it the path name to our raster file. So we will call this CHM underscore harv. And to that name, we'll use raster, parentheses, quotes, data folder, tab complete, raster, tab complete, harv, and then the CHM crop. Because that's the only one. It's good that pulled up the TIFF file. That's right, because it's a raster file, which is a TIFF file. And I'll hit tab complete. We're going to be plotting the raster data. So because we're going to use ggplot to do the plotting, we have to convert this raster object to a data frame. So to do that, we will use the asDataFrame function. So I'm going to use the same start of the file name, only this time append it with, or the same root object name, only this time add df to signify it's now the data frame object, not our raster object. So I will create the object name CHM underscore harv underscore df and use the function asDataFrame. So as.data.frame, open parentheses, and within the asDataFrame function, I'll give it the object name of CHM underscore harv. And because this is spatial data and we want to carry through the XY locations, and we'll use the argument and type XY equals true. Okay, One more thing that we need to load, which are our plot locations, which are stored as a CSV file. So in episode 10, we were able to open this, load the CSV file into R, convert that to a spatial data frame. So we'll do that, those 3 steps here quickly to load that data. So we're loading the plot locations. We'll give it the name plot underscore locations underscore harv. We'll use the function read CSV, so read.csv. And within this function, we want to point to the file. So within quotes, we'll do data. In the data folder, we're looking for harv underscore plot locations. And we're reading in a CSV, and here is the CSV file. So tab complete to finish that file name. So that's us reading in the data. The second part was grabbing some spatial projection information, or the CRS file, from our Harvard data. So I'm going to create a CRS object from the Harvard data using the function stcrs. So the name of that object will be UTM-18 North CRS. I'm using the function st underscore CRS, open parentheses. And within that function, I'm giving the object name point underscore harv. Okay, so that was the second step. And the third and final step for working with this data are to now convert the data frame to a spatial object using the function st_as_sf. Within that st_as_sf function, we want to give it the object that we're converting, the column names that store the XY locations or the coordinates, and the CRS object. So we'll give it those 3 things. So we'll call this object plot underscore locations underscore sp underscore harv. And now we'll use the function st underscore as underscore sf parentheses. We'll give it the object that we want to convert, which is plot underscore locations underscore harv, comma, the coords argument, so COORDS equals, now we need to use the concatenate function. So coords equal lowercase c, open parentheses. Within quotes, we'll type easting. Outside of the quotes, we'll do a comma, do another set of quotes, and inside the second set of quotes, we'll type northing. We'll navigate outside of the parentheses for the C function and do another comma. After that comma, we'll use the argument and type CRS is equal to UTM-18 North CRS. Okay, so now we are all set up to load the packages and the data. I'm going to load everything all at once. You could also load everything in batches. So to run all of this all at once, I'm going to hit this source button here, which will load everything in the script. And it may take a second because it's loading a lot of packages and it's loading a lot of data and doing some spatial conversions. So I'm watching the console as this happens for any warnings. Okay, so it looks like most everything worked fine. It gave me information I was expecting. The place where I got an error, so I'm seeing this red text and I see an error in st_as_sf, where I put in the function, and it's telling me that plot location harv not found. So this is an error message saying you specified the name of this thing, but R doesn't actually know what that is. And so looking back at my script here, I could see that I misspelled an object name. So I didn't use tab complete here, which got me into trouble because I forgot the S on my plot locations. So I'm just going to go back and add an S. And now I'm going to put my cursor at the end of this full function and hit enter. And there we go. And so now my plot locations function ran, and I have my final file. All right, I'm going to go ahead and save this, and then we are all set up to do our raster manipulation. So the first thing that we're going to do in this episode is we're going to crop a raster to a vector extent. And this is important because we often work with spatial layers that have different spatial extents. So the extent of a shapefile or an R spatial object, which represents the edge or the boundaries of the object, might be different for different data layers that you're working with. And all spatial data layers have an extent. There's an extent for points, lines, or polygons. So in this image here, we have the extent for 3 different spatial layers. So we have 3 points here, we have a set of 2 lines, and we have a set of 2 polygons. And the spatial extent for the points and the lines are different because the maximum for the points here, so the highest point is this one, the maximum is lower than the maximum for the line set here, where this point means that the y maximum is actually larger. Now, this is in contrast to comparing the spatial extent for the lines to the polygons, where the spatial extent of these 2 objects are actually the same, because the y min and the y max and the x min and the x max are the same. So we have the same most left to right and most up and down points between the lines and the polygons extents. So in this simplified diagram, we can see differences in extents, but we can also take a look at the differences in extents in the data that we have been working with. So this is a plot of all of the data layers that we have been working with thus far. We have the blue box is the AOI boundary. The lines here are our roads or our paths, which is the line file that we've been working with. The points are the plot location points that we've loaded from a CSV file. And then this green box here represents the spatial extent of our raster layer. So for example, our CHM layer. And the colors around some of these boxes are just bounding boxes that we've added to show kind of the maximum boundary of these boxes. So these are the white points, and then the different colored lines, and then the bounding box, and then the raster. So from the data that you've been working with, you already have different spatial extents. And now we want to reduce the size of our raster layer to only contain the information within this AOI bounding box. So essentially, we are taking like a big cookie cutter. The cookie cutter is our AOI bounding box, and we're punching out our CHM cookie, which is going to be smaller than the full CHM file that we have. So this is a process called cropping. So we are going to crop our CHM raster using our AOI boundary layer. And so we might want to do this when we want to like reduce the file size if we only know we're working in a small area, or if we're creating a map to just focus on that one area. And so sometimes we do have a raster file that's much larger than our study area or our area of interest. And so it's more efficient to crop the raster to the extent of the study area and to reduce the file size to process the data. And cropping a raster can also be useful when you want to create a pretty map, so you don't have a bunch of empty space in your map that's distracting from the area that you want to focus on. So let's go into R and crop our raster. So I'm going to put a comment here, so saying we are going to crop a raster using a vector extent. So we're going to crop, I should say crop our CHM raster using our AOI vector extent. And to do this, we're going to use the function crop to crop the raster. So to use the crop function, we need to specify the raster to be cropped and the spatial object. And if you forget what to put in for these functions, remember you can always look up the help file. So down in the console, I'm going to type $crop. And over in the help file on the lower right, it gives me information about this crop function from the raster package. And so this crop function, if we scroll down to the arguments, requires an X and a Y. The X is the raster object or other sort of spatial object to be cropped. And then the Y is an extent or any other spatial extent object that's going to be doing the cropping. So the X is like our sheet of cookie dough, and the Y is like the cookie cutter. Let's start by looking at the data that we're going to crop. So I'm going to use ggplot to plot some of the data that we currently have. And this will just let us visualize the two data layers before we make that crop. So up in our script, I'm going to create a new line and write a comment. So first I'm going to plot our data to crop. We'll use our ggplot2 code. So we'll type ggplot, open parentheses, follow that with a plus sign. On a new line, we'll use the function GOM_raster, open parentheses. Within this raster function, we're going to give it the data and an aesthetic. And we did this previously in some earlier episodes. So if you can't remember exactly how to do this, and this is moving too quickly, you can always go back and revisit those episodes where we plotted a lot of rasters. So within the geom_raster function, I'm going to type data equals CHM_harv_df, using tab complete to make sure I don't make any spelling mistakes, comma, AES parentheses. Within those parentheses, I'm going to type X equals X, comma, Y equals Y, comma, and fill equals HARV_CHM crop. And again, this fill is the fill matches the name of the file that we loaded. So harv_CHM crop is the name of this raster file. And that name has been assigned to some of the column names in our data frame. So when we converted from a raster to a data frame, it uses this file name. So that's an important thing to remember and to be able to look up if you forget. I'm going to finish this line outside of all the parentheses with a plus sign. I'm going to use the function geom_sf to add our vector layer. So GEOM underscore SF parentheses. Within this, I'm going to give it the data. So data equals AOI underscore boundary harv. Tab complete. I'm going to color it. So comma color equals, in quotes, blue. Outside of the quotes, comma fill equals NA. Then outside of the full set of parentheses, I'll use a plus sign, and I'll finish this plot with chord underscore SF parentheses. So this is a simple plot. So I will highlight all of those lines and run them by clicking Command Enter. And it might take a little bit of time to plot this data because plotting rasters does take a while in R. So especially if they're big rasters with really high resolution where you have a lot of pixels, that plotting is going to take a little bit of time. So here we have our plot of our CHM. And to that plot, we have also added our vector of our AOI boundary. So we can see that these cover the same area. So they overlay each other. So the vector layer is overlaid on top of the raster, but that the extents differ. So the raster has a much larger extent than the vector layer. So back over here in our script, we can now perform the cropping operation. So we will now use the crop function to crop the CHM by the AOI boundary. We will call this crop CHM underscore harv underscore cropped. Use our assignment operator, and then we'll use the function crop. Within the crop function, we're going to give it an X, which is our raster to be cropped, and a Y, which is our vector to do the cropping. So we'll type crop parentheses X equals CHM underscore harv using tab complete, comma Y equals AOI underscore boundary harv. So let's run this line of code. We got no errors, and here we can see in our environment that CHM cropped as a former raster layer has been added. So let's plot the cropped CHM data along with the bounding box of the full CHM extent to show that this crop has indeed happened. Because we've just created a new raster layer, we need to first convert our new raster layer to a data frame to be plotted. And we also need to do another little trick to add the extent of our original CHM plot, our original CHM raster to our plot. And we're going to do this without creating a spatial extent object and without including the actual CHM in the plot. So to get the spatial extent, I'm going to use the function stbbbox. And the BB box stands for bounding box. And this function will extract the four corners of the rectangle that encompass the full raster. So I'll also use the function st_as_sf that we saw in an earlier episode to convert the extent that we just created with stbbbox into a spatial object to include in our plot. And so that whole thing will happen within the geom_sf function in our ggplot code. So I'm going to type out all of these steps and type out all of the ggplot code, and then I'll just highlight what that one pretty complicated function looks like. And this plotting is just useful for us to see what happened. We've already done the crop, so we've already done like the geospatial analysis, but this code is just to visualize the cropping that we've actually done. So first I need to convert, so I'm typing a comment to convert cropped CHM to a data frame for plotting. So we'll call this CHM underscore harv underscore cropped underscore df. Assignment operator, the function as dot data dot frame, open parentheses. Now the object name CHM underscore harv and cropped, comma, xy equals true. So that has converted our raster to a data frame. And now we will plot cropped CHM and bounding box of original CHM. So we're going to do ggplot code, and I will type out all of the code, and then I will explain what each line is doing. So ggplot parentheses, outside of the parentheses, a plus sign. Starting a new line, the function geom underscore sf parentheses. Within this function, we're going to use data equals the function st underscore as underscore sf parentheses. Within this function, we'll use the function st underscore bb box, open parentheses. Within this function, we'll give it the raster object CHM underscore harv. Okay, now we'll move outside of two of those parentheses, so we should be just inside the last closing parentheses. We'll do comma, fill equals green. Outside of the quotations, we'll use comma, color equals green in quotations. Outside of the quotations, type comma, alpha equals 0.2. Okay. Then outside of the most outer set of parentheses, we will do the plus sign to indicate our ggplot code will continue. After the plus sign, hit enter for a new line. We'll now add the raster using the function geom underscore raster parentheses. Within this, type data equals CHM underscore harv underscore cropped underscore df. Using tab complete there. Then type comma, AES parentheses, x equals x, comma, y equals y, comma, fill equals HARV underscore CHM, capital C ROP. Okay, we'll get to the outer part of the parentheses and do our plus sign to keep going with this ggplot code. Then we'll finish this off with a new line where we type chord underscore sf parentheses. Okay, so let's go back and take a look at what we did. I'm going to clean this up a little so it's easier to see on one screen. So I'm hitting enter, but if it's set up on your screen, you don't have to have these breaks in your code. I'm just doing this for ease of reading. So let's take a look at this first chunk here. This first line here is us adding the bounding box of the original CHM raster. So the data we are using for the plotting, so because we're using GeoSF, it's plotting a vector. And the vector that we're plotting is the bounding box or the extent of the CHM raster. Now, when you use STBBBox, it gives you an output that is not a spatial layer. So to make that a spatial layer, we're using the function STAS-SF. And so the combination of these two functions creates a spatial box or a polygon that then we can add to our plot. This fill equals green and color green just tells R that we want both the inside to be filled in green and the outside border color to be green. And then alpha means we're setting some transparency. So it's going to be a little bit see-through. Okay, so that's plotting our bounding box. This geom raster is similar to what we've seen before, and actually the same thing as what we did above, where we're just adding our Harvard raster file as we're specifically adding the data frame, but now we're adding the cropped data frame as opposed to the full data frame from before. So kind of complicated ggplot code, but this part here again was just so we could visualize it. We've already done the hard work of cropping the raster. So let's run this full set of code. Okay, error in no applicable method for STAS-SF applied to an object of class bbox. So this code actually is not running, and I am not sure why. So I need to go back and do some debugging to figure out why this code might not be running. Let's see. One thing that I'm going to do to try to figure this out and try to debug it is to run each of these lines separately. So I'm just going to highlight this text in here and hit Command Return, or I could also hit Run to try to figure out what's breaking this. So Command Return. So that function works. I'm going to go one level out and run this STAS-SF function. Oops. And highlight that whole thing and see if that works. And so this is where it is breaking. Let's see what we can do. STAS-SF. ST. I'm going to look up the help. To see what might be going on. Okay, and after a little bit of sleuthing and online searching and looking at the help file and going back to my notes, I realized that I made a mistake in this STAS-SF function. So what the function I really wanted here was not STAS-SF, but STAS-SF-C. It's a simple fix, but it was something that was really hard to spot, and it caused some frustration. So don't worry if you end up in a situation like this where you feel like everything is right and you can't figure out why it doesn't work. It could just be a simple error like that. Now this function requires, because we have a different type of object that we're creating here, unlike what we had with our previous conversion with our point data, we have to have this, we have to create it as an SFC object. I'm not going to go into more details about that SFC object, but just know that that SFC type object does exist, and in some cases that might be what you want. So now that I've gone and I've fixed this error, I'm going to run the code again and see if we can plot it. Okay, that looks better. So we have created a plot where we have our canopy height layer, so our harv CHM crop, plotted here. And we've also included this extent or this bounding box of our original canopy height model. So we can confirm that we have indeed cropped our CHM to the small area that was our bounding box. I'm going to go ahead and delete that line there. So let's actually make a better plot, because the whole purpose of plotting or cropping our canopy height model was so that we can have a better representation of the data or the CHM values that were that exist within this AOI boundary. So we're going to create a new plot that's just our cropped layer. So leaving a comment saying plot cropped CHM and AOI boundary. So we're going to use ggplot code again, and I'll type out all the code and then explain what each part is doing. So ggplot parentheses, outside of the parentheses, type a plus sign and hit enter for a new line. We're going to first add our raster, our cropped CHM. So we'll use the function geom underscore raster, parentheses, data equals CHM harv cropped df, using tab complete there. After that object name, we'll type AES, open parentheses, x equals x, comma, y equals y, comma, fill equals harv underscore CHM, capital CROP. Outside of that geom raster function, we'll do a plus sign to continue our ggplot code. Now we'll add our AOI bounding box with the function geomSF. Within the geomSF function, we'll give it our data and we'll give it a color and a fill. So geom underscore SF, open parentheses, data equals AOI underscore boundary, comma, color equals quotes, in quotes, type blue, outside of the quotes, comma, fill equals capital NA. Outside of that geomSF function, we'll do a plus sign. And then we want to make this look a little bit prettier. So we're going to assign a custom fill or custom gradient for our Harvard CHM. So rather than having this gradient of light blue to black, we're going to use the terrain colors. And to set this custom terrain colors, we're going to use the function scale fill gradient to n. This will also allow us to change the title of the legend here. So within the scale fill gradient n, we'll define the name or the legend, and we'll also give it the terrain colors. So type SCALE underscore fill underscore gradient. And don't forget the N. So just like the S before, don't forget the N. Open parentheses, type name equals, open quotes, canopy height, outside the quotes, comma, colors equal TERRAIN dot colors, open parentheses, 10. So now outside of those full set of brackets, we'll hit the plus sign, and then we'll finish our plot with the chord underscore SF, open parentheses. So here our ggplot code has added our raster layer. We've added the AOI boundary. We've colored it blue. We'll get in a blue outline and no fill. And we've customized the fill or the gradient of the raster with terrain colors with 10 different breaks, and we gave it the legend name canopy height. So let's run this code. What a beautiful plot. So unlike the previous plot where we had a lot of empty space, here, because we've plotted our two layers that have the same spatial extent, we've reduced that full size of the plot, and this has allowed us to just focus in on the area of interest boundary. So the ggplot will automatically set the extent to be based off of the extent of the largest extent for the layers that you're giving it. And because they were the same for both of our layers, this plot is really constrained to just the areas that we're interested in. We can also see that we changed the title for the canopy height legend here, and that we have this nice set of terrain colors where the higher colors are in white and it goes to orange, yellow, and green. So now let's save this, save all of our valuable work. And the next thing I want you to do is crop some of your own data and plot both of those data. So this will be a challenge for you. So I'm going to introduce the challenge, and then when you're ready to do it, you can pause this video and then come back to the video when you are finished. So the challenge will be you're going to crop the CHM to the extent of the study plot locations. And then you're going to plot the plot locations and the cropped CHM. So that's the challenge for you. Go ahead and pause this video and work on cropping the CHM to the extent of the study plot locations, and then create a plot that contains both the plot locations and the cropped CHM. Okay, so your challenge was to crop the CHM to the extent of the study plot locations and then create a plot that showed both. So the first thing that we're going to do is we're going to crop the CHM with the plot locations. We need to assign this to a new object. So I'm going to call it CHM underscore plots underscore HARV crop. You might have a different object name. That's totally fine. Just make sure it's something informative and useful to you. So I'm going to assign that to that new object name. We'll use the crop function. So crop open parentheses. Our X is going to be the CHM harv. So that's our raster that we're cropping. So X equals CHM harv, comma, Y equals plot locations. And here, remember that we have two Harvard plot locations files. We have our non-spatial data frame that we loaded from the CSV file, and then we have the spatial data frame that we created. So make sure you are selecting the SP data frame. Otherwise, you're not going to have any spatial information for the cropping. Okay, so let's run that line. And we have added that object to our environment. And now let's plot the plot locations and the cropped CHM together. Remember, before doing any plotting with ggplot, your raster data needs to be converted to a data frame. So before we can do any plotting, we need to convert our new data frame, our new raster, to a data frame. So we'll give it the same name, only we'll add a df at the end. So CHM underscore plot underscore harv crop. And this name might be different. Name it whatever you had before. And then we'll use df and use the function as.df data.frame. Within that function, we're just giving it the object CHM plot harv crop and XY equals true. Okay, so we've created that. And now we can create the plot now that we've got our new data frame. So ggplot +, new line, Geom-Raster. We're going to give it data equals our CHM plots harv CHM plot harv crop df, that's a long name, comma AES, x equals x, y equals y, fill equals harv CHM capital CROP. A + for the new line. And now we'll add our Geom SF to add our point layer or our vector layer. So within Geom SF, our data will be, now these are going to be our plot locations. Again, we want to specify the SP1 because that's our spatial data. We'll finish this line with the + and then chord SF, open and close parentheses. All right, so that's our basic plot where we have our cropped raster data and our plot location points. So let's go ahead and run that. Cool. The plot looks great. We have our cropped raster and we have our point locations. Now, you might have added a different gradient or a different fill. So maybe you chose the terrain colors on here. I just chose to plot the default with blue, and I also kept the default legend. One thing we'll notice here is that we have a bunch of points that fall outside of our cropped raster layer. And that is to be expected because our raster layer does not exist where these plots exist. So even though the extent of our point or our plot locations is this large, it's larger than our raster, this crop function isn't going to make up data where data doesn't exist. So let's go back and look at this diagram of all of the extents, all of the layers that we've been working with. And so what we've asked R to do is to take this green box and crop it by the extent of these white points. So the cookie cutter was essentially on the edge of our rolled out cookie dough. And so what we got was just this portion where there was that overlap between our raster and our points. Because there's no raster data up here, even though our extent of these points exist, we don't have any raster data that has filled in up here. So that's why when we plot it, we have the raster data at the bottom where there's this overlap between our points and our raster data. But then we don't have any data up there. It's just plotting the points. Okay, that's great. So go ahead and save your file. Now, the last thing we'll cover with cropping rasters is using the extent function to crop our raster. So far we've used a shapefile to crop the extent of the raster, but we can also create a new extent that's not based on a shapefile to instead crop our raster. So for this next part, I will quickly show you how to create your own extent or your own bounding box and use that newly created extent to crop our raster. So we're gonna create an extent that exists within the AOI boundary. So we'll create an even smaller raster crop. So I'm gonna write a comment saying crop raster based on manually defined extent. The first thing we're going to do is create our new extent. So we will create a new object. So we're going to call it new_extent. And to do that, we will use the extent function, EXTENT, brackets. And within this extent, we're going to give it some numbers. So these numbers are going to be our xmin, xmax, ymin, and ymax. And you can look this up if you use down in the console, if you type $extent and the name of the function. And I spelled it wrong, so $extent. Okay. So extent is part of the raster package. And here you can see the arguments that we can pass it. So it will be these two elements, xmin, xmax, ymin, and ymax. And because our data is in UTM, which has units of meters, these numbers are going to be in meters. So in the extent function, we're going to type 4 different sets of numbers. So let's type 732161.2, comma, 732238.7, comma, 473249, comma, 471333. So 47 and then 1 and then 3, 4 threes. So this is our xmin, xmax, ymin, ymax. Let's go ahead and create that and look at the object of our, or the class of our new extent. So I'm going to run the new extent line, and we've created it in it. And then when we do class new extent, we can see that the class is an extent, which is a type of class from the raster package. Okay, so now we have our new extent. We're going to pass this extent now to our crop function. So if we have the cookie cutter idea again, we're going to have the same CHM piece of cookie dough, but now our cookie cutter is going to be this new extent object. So let's call this new object CHM underscore harv underscore manual underscore cropped. And we'll use the crop function. So CROP, open parentheses, X will be our CHM underscore harv, and our Y will be our new underscore extent. Okay. Now we can run that and we see we've created our new manually cropped CHM. Like we did before, let's just check this out by plotting it. So to plot our raster, remember we need to convert it to a data frame. So plot new raster. So we'll keep our file name. We'll append it with df afterwards. So CHM underscore harv underscore manual underscore cropped. I'm using tab complete there. Underscore df. And we'll use the function as.data.frame parentheses. And within that, give it the name of our newly created raster. So CHM underscore harv. And now I'm going to use my mouse to scroll down to the manual cropped raster. After that, we need to give it comma xy equals true. And I will run that line of code. So now we've created a data frame from our extent. Now let's plot our new raster, but we're also going to add the boundary, our AOI boundary, just to give it some reference as to where this raster exists. So we'll do our ggplot code, so ggplot parentheses +, Let's start with our AOI boundary. So to plot a vector, we'll use the geom_sf function, geom_sf. The data equals AOI boundary harv, so using tab complete. Let's give it color equals, in quotes, blue, outside of the quotes, comma, fill equals capital NA. We're finishing our ggplot line with a plus sign, and now we're adding our raster. So to add the raster, it's the function geom_raster, parentheses. The data equals chm harv manual cropped and the data frame. So I'm clicking it to fill that in with my data frame name. Comma, and then we need to say AES, parentheses, X equals X, Y equals Y, fill equals harv, CHM capital CROP. Probably typed that 100 times by now. Let's finish our ggplot code with a plus sign and our cord_sf function. All right, let's run this chunk of ggplot code and see what comes up. Okay, interesting. All right, here we have our AOI boundary and a really skinny raster. So we've cropped our raster, but I had expected it to be the extent to fall within that boundary object, which did not happen. So that indicates to me that I made a mistake in defining these numbers here. So it looks like because my plot is a lot longer and extends a lot further south than what I had expected, that means that I think my Y min is too small. So I think I screwed up one of my extents in my Y min. So I'm going to go back and because of the help file, I see that the Y min is the third argument here. So 1, 2, 3, I think I messed up a number here. So I'm looking back at my notes and I see that I missed a 1. So the number should be 4713249. And because these are in meters, essentially I have added an extra 10,000 meters to my crop. I think, oh no, I haven't. Well, I did something where I basically had a bigger Y min than I had expected, or a smaller Y min. So I've gone ahead and fixed that. And the lovely thing about having it be a script is I can just rerun all of the code that we just typed. And if I rerun it and I create the raster, the cropped raster again, and I plot it again, I should be able to update this figure pretty quickly after correcting this one fix. So let's do that. Let's go up to our new extent, and I'm just going to run through each line by hitting Command Return or hitting Run. So I'm on a Mac, so I'm hitting Command Return. Okay, new extent. Great, it's still a raster. I'm cropping the raster again. I'm converting it to a data frame, and now I'm running my ggplot code. Okay. That looks better. That looks like what I expected, where my Y min has fallen within this AOI bounding box. So that was a totally understandable mistake. Maybe you did a mistake like that too. But the nice thing was we were able to go back and quickly fix the mistake that we made. And then because it's a script, able to run it all again and get the output that we were looking for. So let's save our file. So far in this episode, we've been able to do the first part of what we set out to do, which was to crop a raster to the extent of a vector layer. So we cropped our CHM raster using our AOI boundary. We also cropped our raster using the point locations. And finally, we cropped our raster using a or manually defined extent. The next thing that we're going to do is extract raster pixel values using vector polygons. So we might want to extract raster values for particular locations, like if we have a plot or if we have like a boundary area that we want to sample from. So it might be useful for us to be able to get all of these pixel values within a polygon, or even like a summary of the mean or the maximum pixel values within that area. That is especially useful if it's done after you've cropped a raster. So let's say you download the full set of neon data, and if you download the data, it comes as a 1 kilometer by 1 kilometer tile. But you know that you don't care about most of that area. Instead, you just want to know like the mean elevation or the mean canopy height of your plots within that full area that you downloaded. So this might be a case where you'd first want to crop the raster to those plots for visualization, and then you can extract pixel values from that cropped raster to use for your summary statistics. So that's what we're going to do now. We're going to extract raster pixel values using vector polygons. So let's go back to RStudio, and we're going to work from the same script. So scrolling all the way down. I'm going to write a comment to signify that here we are extracting raster values within polygon. So to do this, we're going to go back to the extract function, we're going to use the raster package, and within the raster package, we're going to use the extract function. The extract function requires a few different things. So first, it requires the raster that contains the data we're going to extract. It also requires a vector layer that defines like the boundary of where we want to extract. And then we can also tell it how we want the data to be output. So unlike our crop function, where the output was the cropped raster, for the extract function, the output is going to be something that we want. So let's, for now, just have an output as a data frame. So output a data frame. So the output will be all of the values, all of the pixel values saved as a data frame. Okay, so we are going to store this extracted data into a new object. That new object or that data frame will be called tree_height. And then we'll type the function extract. So extract parentheses. We'll start in this function by defining our x, which is our raster. So type x equals chm_harv, comma, y equals AOI boundary harv. So our x is our original uncropped raster. Our y is our vector of our AOI boundary. And then because we want the output of this extract function to be a data frame, we'll use the argument and type df equals true. So let's run this line of code. We see that it's run, it's added a new object to our environment, tree height, and we can check it out using the str function. So str parentheses tree height, and let's run this line. So our tree height object that we just created is a data frame. It contains 18,450 rows or observations of 2 variables. So our variable names are defined here. One is the ID and one is the harv CHM crop. And this harv CHM crop is the name of our file. So when we use this extract function, R extracts the value for each pixel located within the boundary of the polygon being used to perform the extraction. So in this case, we had a single polygon, so our AOI boundary, and we extracted all of the pixels within that. I'm going to go back to one of our other plots where we plotted the raster where we cropped it to the AOI boundary, just to show you what values we're extracting. So here's a plot we created where we have the CHM and then the AOI boundary. So what we have output as tree height is all of these individual pixel values that we see in this figure here. Now, you might want to do a variety of different things with this data, but one thing that we can do is we can create a histogram of the CHM values within this boundary to understand like the distribution of the canopy height at our site. Or because we know this is a tree site, we can understand the distribution of tree height within this boundary. We'll use the ggplot code, and we'll use the function geomhistogram to create a histogram of our data. So let's go ahead and write a comment and say plot histogram of tree height. So we'll do ggplot, open parentheses, followed by a plus sign. On a new line, we'll use the function GEOM underscore histogram, parentheses. Within the histogram function, type data equals tree height, that object we just created. Following tree height, type comma, AES, parentheses. Within AES, we're going to define X equals harv underscore CHM, capital CROP. So we're telling R to take the tree height data and in the X field of this histogram, plot the harv CHM crop. And the harv CHM crop is one of the column or the attribute names that exist in our data frame. Let's do a few more lines here. So use the plus sign for a few more lines. And we're just going to give this a title and an X-axis label and a Y-axis label. So next, type GG title, parentheses, and within the title or within the function, use quotes and type histogram of CHM height values. And that will be in meters. Finish the line with a plus sign, and we'll give it an XLab, parentheses, in quotes, we'll type tree height. Finish the line with the plus sign, we'll give it a YLab, in quotes, type frequency of pixels. And let's run this ggplot code. So I had an issue with my GG title. Let's see. Could not find the function GG title. GG title. So that's strange. I misspelled it. So GG title, TITLE. Okay, let's try it again. Okay, we got our normal message with a histogram, which is saying that it used some bins for us. So it defined the number of bins to be 30. That's fine for this case. We just wanted to get a quick histogram. And now we can see the distribution of the tree height that we have from within our AOI boundary polygon. So here we can see it's maybe a peak distribution just around under 25, maybe around 23 meters, but that it ranges from almost 0 to upwards of 30 or even 40 meters. So that's a really nice way to see the data that exists in a raster file. So again, you could summarize the distribution of canopy height or tree height within a particular plot or within a particular boundary. In addition to plotting, we can also get some summary statistics of this tree height data that we created. So we can go back to some standard functions that we've used for non-spatial data, such as summary, to get a summary of this data. So we're going to type summary, parentheses, and give it our object name of tree height. And we just want to look at the CHM value. So we'll do $ and highlight the Harvard CHM crop. So let's run this line. And because we're not assigning it to anything, the output is put in the console. So here we can see the min, the median, the mean, and the max, and the first and third quartile ranges. And this corresponds to what we're seeing in the histogram as well. Let's go ahead and save that. So that extract function, because we defined df equals true, it gave us all of the pixel values. So it gave us every single pixel that exists in our AOI boundary object. We were then able to do a histogram to see the distribution and then get some summary statistics from that data. We can also get some of the summary statistics directly from the extract function. So let's say you didn't care about the distribution, more so you just wanted the mean CHM value within that area. Well, rather than defining df equals true, you can specify that you want to calculate a summary statistic from within that function. So I'm going to write a comment for us to now extract the mean CHM from the AOI boundary. So we're going to use the same extract function, only create a new object, and that new object will be the mean tree height AOI. We'll use the same extract function, so extract, parentheses. Our x will be the same, so x equals CHM underscore harv, comma, y equals AOI boundary harv, comma, and now rather than df equals true, type fun equals mean. So this doesn't mean that being mean is fun. It means that we're specifying a function to use to calculate this data, and the function is going to be calculating the mean. So we can now run this line. And let's take a look at the output. So type the mean tree height and take a look. So here this mean is calculated as 22.43018. We can compare that to what we did before, where we extracted all of the values and then used summary statistics. So if we go up here, we can see that our mean was the same at 22.43. So 22.43. So that was two different ways of getting the mean CHM pixel values from the AOI boundary. So what we just did was we extracted raster pixel values using a polygon that defined the pixels that we wanted to extract as a data frame or to calculate a mean summary statistic or a summary statistic. We can also use point locations or XY coordinates to extract from raster data. So here we're going to use the same CHM raster file, and instead we're going to give it a point location, so an XY location that corresponds to some area within that raster file. If we give it a point location, then we can define a buffer region from that point. Doing that, we'll basically look at all of the pixels within that buffer region around that center point, and it will extract all of the pixels that touch that buffer region. So in this way, rather than having, for example, like a square polygon, we are getting this circular area of this buffer and all of the pixels that touch that circular area. So let's go back to RStudio and do this with our Harvard data. So I'm back in RStudio in my script. I'm going to give us some room and type the comment, extract raster data using X, Y locations. So we can extract pixel values from a raster by defining a buffer or an area surrounding individual point locations using the same extract function that we did before. To do this, we will define, we can define a summary argument as we did before. So we can say function equals mean. And then we can also give it a buffer distance that we want to use around that point. And that buffer distance is going to be in a particular unit. And that unit will be specified based on our units of the raster data. So because we are in UTM for these raster data, that buffer that we're giving it is also in UTM, which is in meters. So let's use the same extract function, and this time extract the CHM data based on our Harvard point location. So we're going to create a new object. We'll call it mean underscore tree underscore height. And now rather than AOI, we'll say height tower. So we're extracting the mean tree height around the tower. Our assignment operator, and then we'll use the extract function. Within this extract function, we're going to give it 4 things. The first is going to be, I'm going to write some comments. We're going to give it 4 things. First is going to be the raster. The second is going to be our point location. The third is going to be our buffer, or the size of the buffer. Size of the buffer. And then the fourth is going to be our summary function. Okay, so let's go back into our raster function and define those 4 things. So first type X equals CHM underscore harv, comma, Y equals point underscore harv. So we have our first 2. Do a comma. I'm hitting enter here, but you can continue on the same line. We'll give it buffer equals 20, comma, and fun equals mean. So now we've defined those 4 parts of our extract function. I'm going to run this line, and we've output our object. Let's take a look at this object we've just created by typing it in the script. So mean underscore tree height tower. Run this line to take a look at our object. So in the console, it's output our summary value. So the mean tree height within 20 meters of our tower location is 22.38812. That's cool. So now we have a single value that represents the mean tree height around that tower. The next thing that we're going to do, and this will be a challenge, is to now extract height values around each of our, or within each of our plot locations. So the challenge will be for each plot location within our Harvard site, extract the mean value within a 20-meter buffer of each point. So I will type it, the challenge. You are going to extract the mean tree height value within 20 meters of each plot location. And you're going to create a plot showing the mean tree height. for each plot. Again, here, plots and plots, it gets confusing when you're talking about field plots. You're going to create a GG plot showing the mean tree height for each field plot. Okay, so go ahead and pause this video, and when you're done, unpause the video and we'll go over the solution. Okay, so we're first going to use the extract function to create a new object that is the mean tree height for all of our plots. Let's create a new object and call it mean_tree_height. And now we want to specify it's the plots from Harvard. You may have called it a different file name. That's totally fine. Just make sure it's something informative for you. So we're going to use the extract function, and we're going to use a combination of arguments that we did in the previous two examples. So I'm going to actually create a comment up here. So use the extract function. We're actually going to give it 5 different pieces of information. So we're going to give it the raster, as we did before. We're going to give it our plot locations. We know that we want the mean, so we're going to give it the mean function. We also know that because these are point locations, we need to give it a buffer. So we're going to give it the buffer width. And because we want to plot that data and do something with it, we want to output that information as a data frame. So we're going to say output as data frame. So those are the 5 pieces of information that we'll use within our extract function. So let's start our extract function, extract, parentheses, x equals CHM harv, and our y equals our plot locations. And remember, we have 2 different versions of our plot locations. We have to remember to give it the spatial plot locations. Okay, I'm going to hit comma and type in the rest of the arguments. And now for these arguments, you may have them in a different order. So maybe you chose to do like the buffer width before the mean function. That's usually okay in R as long as you specify the name of that argument. So for each of these arguments, I'm going to put the name equals whatever I'm defining as that argument. Sometimes you'll see that we don't use the name of the argument, but that's in maybe like some more simple cases where R is expecting a certain order. But for here, I'm going to give it the name of the argument and then what's defining it. But you might have them in a different order. And as long as you've named the argument, that should be fine. Okay, so after my x and my y, I'm going to say fun equals mean, comma, buffer equals 20, comma, and df equals true. Okay, so that's all of my extract arguments. I'll run this function. You can see it took a little bit longer to plot or to extract because we're now extracting a lot more data. And just for fun, I'm just going to look at a summary of that data. So summary mean, tree height, plots harv. Okay, so in that summary, I can see I have 2 columns. I have an ID 1 through 6. Oh, no, an ID 1 through 21. And I have values for the harv CHM crop. I can also look at the structure of the data, mean, tree heights, tower. Oops, I did it wrong. Mean tree height, plots, harv. And then this is a little bit more informative because I can see it's a data frame with 21 observations of 2 variables. So that's good. That makes sense. That indicates to me that I have 21 observations, which matches my 21 plot locations. It looks like I have a number for each of those plot locations. And then I have a variable, or the extracted variable for each of those as well. Okay, so the second part of this challenge was to plot. So now I'm going to plot the mean CHM values. To do this, I'm going to use ggplot. And we're not plotting any sort of spatial data here, so we're going back to some ggplot basics for just plotting our data frame. So ggplot +. For this, I'm going to actually define my data within this ggplot first function itself. So within the first ggplot function, I'm going to say data equals the mean tree height for our plots at Harvard. And I'm going to define the columns with my aesthetic. So after the mean tree height plots Harvard, comma AES, the first argument for X is going to be ID, comma, Y is going to be Harv underscore CHM, capital CROP. I'm going to finish that line with a plus sign and hit return to start a new line. I want to create a column or a bar chart. So I'm going to use the function GEOM call. And because I've defined all of my data and my aesthetic up here in the first ggplot function, I don't need to put anything else in this geom call or function. I'm going to give it an informative title. So GG title, in quotes, mean tree height at each point. Complete that line with a plus. Give it an XLab in quotes, which is my plot ID. Complete that line with a plus. Give it a YLab in quotes with tree height in meters. And because this is the last line of my ggplot code, I do not have to end with a plus sign. So let's plot our data. All right, so a couple things happened here. One is I got a little warning. It wasn't an error, but it was just a warning saying remove 9 rows containing missing values. That indicates to me that I probably had some missing data or some NAs. We can check that out here in the plot as well. So here we have our plot where it's the mean tree height as each point. I had a little typo there. It should be at each point. And we have on our x-axis the plot ID, so 1 through 21, and then our mean tree height in meters. And so here we can see the mean tree height as the height of these columns for each of our 21 plots. And there are cases where we are missing data. So it looks like we're missing 9 rows that contain NAs. And if you remember back from our extent exercise, we know that there's some plots that fall outside of the CHM raster data. So this is not surprising to us because we know there's some points where we just don't have any raster data. So the fact that we're missing data is fine. So in this episode, we've done a lot. We've extracted, we've first cropped our raster to the extent of a vector layer in a variety of different ways. And then we've also extracted values from a raster based on a vector overlay. So we've done that both for having a vector overlay and we've done that for using point locations. So both of these tasks have been able to get us a more usable raster. One, because we've reduced the extent to focus on just an area of interest that we want. And then I'll actually extract the values from that raster and take the data out of that raster for a particular area of interest. And then from there, we're able to perform some summary statistics and some plotting. And that's all really useful because raster data contains some really important information that you might want to use for knowing about your study area. So for example, here we had a canopy height model, which gave us the height of the canopy for the whole surface. But because we weren't necessarily interested in that whole area, we could just extract the canopy height for particular areas of interest. And all of a sudden that raster data went from being like a pretty picture that we could look at and create maps to understand our area, to actually some data that we could then summarize and then use for other analyses.